Hi everyone, this is Shane doing the exam, practice exam key video here. So hopefully you can see this well. I'm gonna plan on doing every problem, but we'll see. Sometimes I get tired and sometimes I am afraid that this video just won't upload because of the size of it. Anyways, I'll get going. Number one, why is the cube root of -8 not an imaginary number? So the cube root basically means, so I'll say because when you have the cube root of some number, and if that equals a number like c, then this means that c times c times c would be x. And if you have an odd number of multiplications, then if c is negative, then x will be negative, right? So, for example, if you have the cube root of -8, like we do here, this is -2 because -2 times -2 times -2 is -8. So all of this would be a part of my response. All right, so number two, I think this is a hypothetical student here. I think the square root of 18xy cubed simplifies, it should say, to 3 absolute value y times the square root of 2xy. I'm writing down all these problems. Let me just make sure I have that written correctly. Yep. So basically one way to do this would be to actually simplify it yourself. So the square root of 18xy cubed. So what I want to do, since it's a square root, is I want to pull all the perfect square factors out of this radicand. So this 18 has within it a 9. So 3 squared is a factor of 18. So that's my 9 times 2 would be the 18. X, there's no perfect square factors in x. The power is too small. Y cubed, I can think of as y times y squared. So these two things, out of those, we'll get a simplification. I'll slide those up front. So we have the square root now of 3 squared y squared times 2xy. And now using the product rule, I can split this up right there. So I can say the square root of 3 squared y squared times the square root of 2xy. If I have the square root of 3 squared y squared, I can essentially take the power out of both of these. So we can say the square root of 3y all squared times the square root of 2xy. When this cancellation occurs, I need the absolute value, right? I'm going from even to potentially an odd. So we have absolute value of 3y, since that was an even cancellation, square root of 2xy. The 3 is just a 3. It has no potential to become negative, right? So it doesn't need to be in this absolute value. So we can finally say 3 absolute value y times root 2xy. And just looking at what the proposed solution was, this looks correct. 3y root 2xy. So is that correct? Yes. And because of all these reasons down here. All right, so number 3, true or false, we are allowed to have negative numbers inside of even index roots. If so, why? If not, why not? So by allowed, I mean, do those result in real numbers? And they don't result in real numbers. So we are allowed to have negative numbers inside of even index roots. This is false, because an even number of multiples always results in 0 or positive outcomes. So that's the first page. 1, 2, and 3. Here's number 4, where we're starting to simplify. So simplify, it says use absolute values only where necessary. So the first one I have is a square root. So I want to think of, okay, how do I get all the perfect squares out of x to the 10th? X to the 5th squared is the same as x to the 10th because powers to powers multiply. After this cancellation occurs, it's going even to odd. So when it goes even to odd, what I mean is even to odd. Then I do need this set of absolute values. Okay. For the next one, we have a 5th root. So that means I'm looking for all perfect 5th powers of these objects here. So not looking to write things as something squared. I'm looking to write these things as something to the 5th power, if possible. So negative 96. Let's see, I'm going to start dividing 96 by perfect cubes. So the first perfect cube is 1, the second perfect cube is 8. So 96 divided by 8 is 12, actually. I was saying cube, I should have been saying 5th. So let me redo this. Instead of 8, so 96 divided by, I guess, 32. Yep. So one thing to note, 2 to the 5th is 32. And 32 divides 96. That happens 3 times. So I'm going to use those facts to rewrite 96. And also I'm going to simultaneously rewrite these others. So this is the same as the 5th root of, let's see, 2 to the 5th. That's 32. And then times, maybe I'll write negative 2 to the 5th. Negative 2 to the 5th, that'll be negative 32. And then times 3, that'll be negative 96 right there. I have t to the 5th, so I'll just write t to the 5th. That'll actually simplify outside. C squared to the 5th, right? I'm matching this index. 9, I have h to the 9th. In other words, I can write this as h to the 4th times h to the 5th. Right, so all these things will simplify and the other stuff won't. So we have now the 5th root of, let's see, I'll bring the 5th power outside also. So I have negative 2t c squared h to the 5th. Right, everything I had negative 2, right, negative 2 t c squared, h, each of those things were being raised to the fifth power. So I have taken that fifth power outside. Then I have times 3, what was left behind is 3h to the fifth. Sorry, h to the fourth. Then I can go ahead and split up using the product rule there. Okay, so I have the fifth root of negative 2t, sorry. So that was the fifth root of negative 2t, c squared h, all to the fifth, times the fifth root. Don't forget to write the fifth root, right? If we're splitting this up across that fifth root, we have now 2 fifth roots. It's not like a fifth root and then a square root or something. So we'd have the fifth root of 3h to the fourth. And now this cancellation can occur. It's odd. I don't need to think about absolute value. So I have negative 2t c squared h times the fifth root of 3h to the fourth. All right, part 3. So I'm going to simplify. First, it looks like the product rule can be applied. So I can write the square root of 3x to the negative fourth times 6x to the 10th. Okay. So actually multiplying, I can say 18x to the 6th, right? I'm adding negative 4 to 10. So negative 4 plus 10 gives me this 6. And now I'm trying to simplify this thing. Inside of 18, I have a perfect square of 9. Inside of x to the 6th, I have a perfect square of x cubed. So simplifying those, I have the square root of 3 squared times 2. This is the 18. And then times x cubed squared. This is the x to the 6th. So everything with the square slides up front. So I have 3x cubed all squared. And then I just had the root 2 left behind, or just the 2. Product rule. So I have the square root of 3x cubed squared times the square root of 2. And now this cancellation occurs. I'm going from even to odd, right? This even index to odd. So I do need absolute values. So absolute value 3x cubed root 2. And the 3 does not need to be inside of the absolute value. And the instruction was use absolute value only where necessary. So I will take that 3 out, and I'll say 3 root, sorry, not root, but absolute value x cubed, and then times root 2. All right, part 4. Basically, I need to distribute, and then I'll do some simplifying. And actually, I can do some simplifying right up front if I want, right? I have the cube root of something with y cubed in it. So you could just simplify even before you distribute. So just to do that simplification maybe a little more quickly, since I have a cube root of something cube, I can just write that as that something. So we'll have a y times the cube root of 2. Right, this simplification will lead to this. It's an odd index, so no absolute value going on. And now I can go ahead and distribute this. So this is cube root. I'm basically using the product rule to say cube root of 2y cubed right? 2y times y squared, 2y cubed. Distribute here, I get plus y, it's a plus y, and then I have the cube root of 2 times 2 times y, so 4y. Here, again, another cube root of something cubed, so I can say y times the cube root of 2 plus y times the cube root of 4y. So that could be it. You could also factor the y out and say y times cube root 2 plus cube root 4y if you wanted. I don't care which one you prefer. Okay, this one I might run out of room, but we'll at least get you started on it. So cube, meaning I need to multiply this thing by itself 3 times. So I'll have root a plus root b times itself, root a plus root b times itself, root a plus root b. You get a sip of water. It's not a beer, I promise. Okay. So first set of foiling, I'll take root a times root a. That will be the same as square root of a squared, right? Then I have root a times root b. That will be the same as root ab. And then I'll have the inside, I'll have another plus root AB. You could write it as BA, but same as AB. And then root B times root B, I'll have root B squared. And then this is still being multiplied by root A plus root B. So simplifying these in the middle, I can say, and also notice I have the square root of a squared, that's absolute value of a. And I have the square root of b squared, that's absolute value of b. And then adding these like terms. So I have absolute value of a plus 2 root ab. And then plus absolute value of b. And then this all needs to be multiplied by root a plus root b still. Okay, so I'll need to distribute basically root a into this, this into this, and then this into this. So I'll have absolute value of a, root a, right? Absolute value of a, root a. Absolute value of a, root b. So this one is done. 2 root ab times root a. This will be plus 2 root a squared b. Right, product rule is happening there. And then this one times root b, I'll have plus 2 root a b squared. So this one is done. And then absolute value b times root a. That's all I have. And then absolute value of b times root b. Okay. Let's see, I might need another sheet of paper in a second, but we'll see. Here I have root a squared b. So what we can do is actually factor out another root a squared. So I'll have another absolute value of a here. So I'll have absolute value of a root a, I'm just writing that down, plus absolute value of a root b, just writing that down. And then here I'll have plus 2 absolute value a root b. Here it'll be kind of similar but opposite. I'll have plus 2 absolute value b root a. Here I have what I have, absolute value b root a plus absolute value of b root b. Okay, so it looks like we might have some like terms. Let's look for them. I have absolute value of b root a. I have 2 of those here. Well, I have 1 here and 2 here. So I'll have 3 total. I have absolute value a root a here. I don't have another one of those, so I'll just write it down. Absolute value of a root a. That one's done. Absolute value a root b. I have 3 of those right here. Right? These are like terms. So I have plus 3 absolute value of a root b. So these 2 are done. And then in a similar way, I have 2 copies here and 1 copy here. So I have plus 3 absolute value b root a. And then I only have 1 of this type. So plus absolute value b root b. Just looking at, okay, I believe that's it. Okay, so on to number 5. Okay, all right. So number 5, rationalize each denominator, use absolute value where necessary. Okay, so rationalize meaning we're going to use the conjugate a lot of times throughout these types of problems. So the conjugate of root 5 minus 2x will be root 5 plus 2x. So what I do to the bottom, I'm going to also do to the top. Since I don't want to actually change the value, this is just a strange form of the number 1 right here. So I'm not actually changing this number's value. I'm just re-representing it through use of this conjugate, and therefore I'm rationalizing. So with the use of the conjugate, you will always get this difference of squares thing to appear. So you can use that to simplify in a lot of cases. So I could say root 5 plus 2x, basically just 1 times the numerator. I'm multiplying straight across. And then I'll have, if I use this shortcut, a for this situation is root 5, so I'll have root 5 squared. All right, that's what it says to do. Just go ahead and square a if you have a there and there, which we do here and here. So I'm squaring root 5. And then it says to take away b squared, so 2x all squared. So I have root 5 plus 2x over, so the root 5 squared cancels, so I get 5 minus everything needs to be squared, so I'll have 4x squared down there. Let's see. I'm wondering if we should continue this. So if you notice, this one, if I separate that, I'm just going to get this. I think we're good here. So I'm just looking at this like, do we want to factor this now and then get a cancellation up top? But we don't. We would just go in a circle there. So this would be it. That's rationalized. So part 2, again, we're just looking at denominators here. So the conjugate of our denominator will be exactly what it is, except we just change the sign in the middle. So what I do to the bottom, I have to do to the top, so I don't actually change the value of anything. Up top, I'll just actually bring those together. So I'll just adjoin them, meaning I'm not actually going to multiply those out. It doesn't really require that of me. And then again, just to use this shortcut, I should have a squared minus b squared. So in other words, root 2, I don't know that I need parentheses, I'll just write it as root 2 squared minus root 3 squared. So in other words, we're getting 9 plus root 5 times root 2 minus root 3 over 2 minus 3. In other words, negative 1 on bottom, I can just think of this as negative 9 plus root 5 times root 2 minus root 3. All right, dividing by negative 1, same as multiplying by negative 1. Okay, so running out of room, but we'll just keep going. Cube root of negative 8 over 81 v to the 7th. So again, I'm trying to get all the perfect cubes out of this. And also I'm trying to rationalize the denominator. But what I'm going to start with is just simplifying. So this would be the same as the cube root of negative 8 over the cube root of 81v to the 7th. The cube root of negative 8 is negative 2. The cube root of 81, so 3 cubed times 3 is 81. Right, 3 cubed times 3 is 81. So I can use that. So the cube root of 3 cubed times 3, v to the 7th I can think of as v times v to the 6th. Okay, so now everything that's a multiple of 3 will slide out front. So 3 cubed, and then I'll write v to the 6th as v squared. Sorry, I'll save that step. So I have 3 cubed v to the 6th, and then I'll have times 3v, right? Basically this one and this one have come out front and 3v are left behind. The product rule can happen, and I can also bring the power of 3 outside of both of these. So I'll say negative 2, the cube root of 3v squared cubed. Hopefully you can see that. So keep in mind, I had 3 cubed, so I have that out here now. Right, here's the 3 cubed. And then I had v to the 6th, here's v squared cubed. Right, this is multiplying to make that 6. Then I know that I also have the cube root of 3v, right? This was left behind. When this takes place, I do not need to think about absolute value, so I'll have negative 2 over 3v squared times the cube root of 3v. Keep in mind the problem asked us to rationalize, so meaning I still want to get this root taken care of. I don't want any roots in the denominator. If you look back at the ones that we've rationalized, We went from something that had a root in the denominator to something that didn't. That's a rationalization, right? We went from something that had a root, a couple roots in the denominator, to something that didn't, right? So we're still wanting to rationalize this and take care of this cube root of 3b. So what I want to do is multiply by the cube root of 3 squared v squared. Cube root 3 squared v squared. That's because I just have a 3 and a v. So to get something cubed in here, I need to adjust, right? I'll have 3 cubed after this multiply happens. I'll have a v cubed after this multiplication occurs, which is good. So now -2 3v squared cube root of 3 cubed v cubed. This would equal -2 over 3v squared, the cube root of 3v all cubed. Now, I also have, I don't want to forget that I multiplied it up top. So let me include that. I'm just writing 3 cubed as 27. Okay, so now this can go away. Sorry, this should be squared. Yeah. A lot of details here. So I had 3 squared, not 3 cubed. All right, so this should be 9v squared. A lot of moving parts. So now this cancellation occurs. 3v is left behind. So I can adjoin that with this 3v squared and get -2 cube root 9v squared over 9v cubed. Not the most fun I've had today, I admit. All right, so part 4, more of the same. I want to rationalize. So since I have a cube root again, I want to get everything to have a cube power in the denominator here. So the way that I would do that would be to multiply by some type of cube root, top and bottom. But the thing that goes inside of here, and that's what I think, if you're still struggling with this stuff, it might be this step. To figure out what question mark is, I look at my index. Sorry, I just hit the camera. So I look at my index, and what I want is to build up everything inside of here to have that power on it. 3 is currently to the first. Y is currently squared. Z is currently to the first. So to adjust accordingly, I need a 3 squared. 3 squared times 3 to the first will be my 3 cubed that I want. I need a y. Because I have a y squared already, I only need a y. I have a z, I need a z squared. So what I do to the bottom, I then need to do that exact same thing to the top. And now this is my strange form of 1 that I'm multiplying this by to rationalize. So we have the cube root of, well, I'll go ahead and bring these together. This is the cube root of 81, right? 9 times 9, 81. And then I have x squared, y, z squared, right? I'm bringing everything in here into here. And just make sure that went okay. This looks okay. And then this is over what we created. This cube root of 3 cubed, y cubed, z cubed. Okay, so cube root of 81, again, just like we saw up here, wherever that was, we'll get this 3 cubed times 3. So I can say cube root of 3 cubed times 3. That's the 81, and then I'll have y squared, or sorry, x squared, y, z squared. None of that will come out. And then down here, I get this full cancellation because I'll have the cube root of 3y, z, all cubed. Right? All these powers are shared, so I can bring that totally out here, outside of the parentheses. This will occur now. No need for absolute value since this is an odd index. And a 3 will come out, right? Cube root of 3 cubed means I'll have 3 cube root of 3x squared y z squared over 3yz and the 3's can cancel. So finally, we can write the cube root of 3x squared yz squared over yz. Okay. So number 5. All right, I have a 6th root. I have a 64. Let's kind of see what we have. 64 is, I believe, 2 to the 6th. So rather than making a 64 to the 6th or something like that, I can actually already consider 64 as something to the 6th. It's 2 to the 6th. So I'll make that adjustment. So 6th root of 2 to the 6th, x cubed, y cubed. So this is another way of thinking about what we originally had. And now I'm thinking, okay, I need to build up to match this index. So building that up, I already have my 6 on the 2. I have a 3. So I need to multiply by the 6th root, right? They need to be both 6 roots. Give myself more room. So the 6th root of x cubed, y cubed. So what I do to the bottom, I have to do that same thing to the top. These things are multiplying, by the way, and these things are multiplying. So x cubed, y cubed. So 4 times the 6th root of x cubed, y cubed over what we created here, the 6th root of 2 to the 6th, x to the 6th, y to the 6th. So I have 4, the 6th root of x cubed, y cubed, over the 6th root of 2xy all to the 6th. And now when this cancellation occurs, that's an even index going to odd powers, even to odd. So absolute value on. Okay, so 4 6th root of x cubed, y cubed over, the 2 doesn't need to be an absolute value, so I'll bring that out. So I have 2 absolute value xy, and then 2 goes into 4 twice. So I can finally say 2 6 root x cubed y cubed over absolute value xy. All right, that's number 5, just like that. So number 6, I'll probably do just a few of these on the video. I'll make sure I do some of the difficult ones. So I'll do number 6 part 1. I'll do number 6 part 2. And then maybe I'll do at least number 6 part 4, and then we'll reassess. Definitely I'll post pictures alongside the video of solutions to everything, but at least on the video I'll do these 3 from number 6. So number 6 part 1, basically with all these you want to isolate the root. This is a square root. So I want to get this square root alone. What I'm going to do is, after that's alone, I'm going to square both sides to eliminate that root. Whenever you use an even power to solve, you need to check your work. If you're using an odd power to solve, it's a good idea to check your work still, but you're not going to get extraneous or spurious solutions with those cubes, but you still may get incorrect solutions, quote unquote. So it's always a good idea to check. So what I'll do is isolate the root by subtracting 2. So I get x minus 2 equals the square root of x minus 2. Okay, then I'll square both sides. I need to square the entirety of both sides. Now I'm foiling x minus 2 times itself, right? Here, this cancellation occurs. I'm not going to write absolute value. What I'm going to do is just check my answers at the end. Okay, so x squared outside minus 2x inside minus 2x, right? I'm just quickly foiling this out. Plus 4 equals x minus 2. Combine like terms. We often with these problems, we're starting with this radical equation, and then what we're leading to is eventually a quadratic for which we're using our factoring skills on and all that good stuff to solve. So I'm going to pick a side for 0. I'll pick the right. I'll just first combine these like terms. I have negative 4x plus 4 equals x minus 2. I'll go ahead and subtract and add. So this will create my 0 on the right. So I have x squared minus 5x plus 6 equals 0. Right? So from this radical equation here, we now have a quadratic. And what I'm thinking here is, oh, I hope this thing factors so I can solve this, because factoring is really the main approach that we have. So we're looking to multiply to a 6 and add to a negative 5. Okay, so let's see. How do we do that? Just checking my work also at the same time that we're looking at this. Yeah. Negative 2, negative 3. Right? So since there's a 1 here, I can quickly write down that factorization. So I can say x minus 2 times x minus 3 equals 0. So in other words, x minus 2 equals 0, or x minus 3 equals 0. So in other words, if I add 2 and add 3, we're getting potential solutions as these. Potential because I squared back here to solve. So right here, a kind of red flag went off in my mind where, I don't know if this will make sense, but there's a red flag there. Sorry. When you square, you always need to check your work. So any even power, you'll need to go back and check your work. Okay, so there's that red flag saying, all right, these may be solutions, but we really need to check. So is it true? So this is my check. So is it true that 2 equals the square root of 2 minus 2 plus 2? Square root of 0 plus 2 is 2. True. So at least we have one solution. Is it true that 3 equals the square root of 3 minus 2 plus 2? Right, is this true? So plugging in, right? I'm plugging in my 3 now for x. So 3 equals root 3 minus 2. This is 1 plus 2 equals 3. These both work, actually, in this case. That's number 6, part 1. Number 6, part 2 is a cube root situation here. Again, the principle is the same. I want to isolate this root. So I will subtract 8. After doing that, we'll have the cube root of 5x plus 1 equals negative 4. Maybe I'll kind of bring this over here a little bit. Hope that's helpful. And since this is a cube root this time, I'm now going to cube both sides. So this cancellation will occur. I'll have 5x plus 1 equals negative 4 cubed is negative 64. And then solve for x. So subtract 1, subtract 1. I have 5x equals negative 65. Sorry. Divide by 5. Negative 13 that is. So x equals potentially negative 13 if there are no mistakes. I know that there are no red flags because I didn't use an even power this time. I used an odd power. Still a good idea to check though. So the cube root of 5 times negative 13, if I add 1 to that and then add 8, is this equal to 4? All right, so on the calculator, I'm now typing this in. So cube root, you can find that right here. So right there is the cube root. So I'll need to go shift square root, and then a cube root pops up. 5 times negative 13. Then add 1, scroll outside of the root, add 8. We're looking for a 4, and we do have a 4. So this means that 13, negative 13, that is the solution. So that was number 6, part 2. I'm skipping number 6, part 3. I'm going on to number 6, part 4. I'll do a solution for this separately and post it alongside the video, of course. So on this one, we have 2 roots. Still, with the 2 roots, you want to isolate at least one of the roots. And then what you may need to do is do 2 rounds of squaring. So I do have this root isolated, so I will square both sides. So in other words, on the left, we'll have root x. If this thing is too close now. kind of focusing on my hand, I'm seeing. So plus 2, and then root x plus 2, that'll be happening on the left, and then this cancellation just takes effect. Right, foiling this out now. So root x times root x, that'll be the square root of x squared. Root x times 2 is plus 2 root x. 2 times root x is 2 root x. 2 times 2 is 4. And I still have x plus 16 over here on the right. Okay. This cancellation occurs. Technically, I would need absolute value, but we're going to check our answers anyways. So plus 4 root x plus 4 equals x plus 16. It still has a root in this equation. So again, what I'm now doing is doing another round of isolating a root, and now I want to isolate this root, so when I square, now I'll have no more roots. So I'll subtract x, I'll subtract 4. So what I have is 4 root x on the left, right? Everything else is gone on the left. Here, x's are actually gone, and I have now equals 12. Right, divide by 4 to fully isolate root x. So I have root x equals 3. And now finally squaring for the second time. And I get x equals 9, potentially. I say potentially because we squared here and we squared down here. So definitely a red flag is going off. And we do need to check this. All right, so let's do the check. It may be that we have no solutions. It may be that this is the solution, right? So we do need to check this. So is it true that the square root of 9 plus 2 is equal to the square root of 9 plus 16? So 3 plus 2 equals the square root of 25. That is true. 5 equals 5. So x equals 9 is good for this one. So that was part 4 of number 6. I'm going to do part 5 and 6 separately, and also part 3 separately. So you can check out the document that's attached near the video for those. All right, so number 7. This is our application, or one of our application problems. It says the height h in feet of a redwood tree can be modeled by this function, where t is the time in years after being planted in the ground. How old will the tree be when it is 300 feet tall? So you might be wondering, okay, what do I do with that 300? Well, h is the height, right? T is the age of the tree. So plugging in that 300 goes in for h, not for t. So we're looking for t, the age. So just like before, I want to isolate the root. So I'll divide by 20, not subtract by 20, right? This is 20 times root 3, so I'm dividing that away. 300 divided by 20 is 15, of course. So 15 equals the cube root of t minus 1. Now I do have the cube root isolated, so I'm going to cube both sides. So cubing. So 15 cubed is fairly large. That's 3,375. And now I have t minus 1. Right, this cancellation took effect. And then add 1. So it looks like I'm getting 3,376 equals t. So how old will the tree be when it's 300 feet tall? It'll be 3,376 years old. Part B of this application is different context. So kind of totally different. No more trees. The temperature T of a frying pan in degrees Fahrenheit can be modeled by the function, this one we're given, T of x. Here, x is the number of minutes the pan has been sitting on the burner. How many minutes until the burner is 250 degrees? So again, that 250 degrees is not going to go in for x, it's the temperature. And then we're going to search for the x, the number of minutes that made that temperature occur. Okay, so 250 equals 5 times 1.8x raised to the 1/2 power plus 62. If you want, you can think of the 1/2 power as a square root. So it would be totally equivalent to write this. All right, the 1/2 power, same as the square root. I still have the 62. So again, just like the previous couple, we want to isolate the root. Right, in this case, I'm going to use a square. So subtract 62. 250 minus 62 is 188. So 188 equals 5 root 1.8x. Divide by 5, right? This is 5 times the root, so I'm dividing it away. So I have 188 over 5, I'm just going to leave it like that, equals the square root of 1.8x. Square both sides to get rid of the root. So I have 188 over 5 squared equals 1.8x. Divide by 1.8. And this one says round to 1 decimal place. So what I'll do now is type this into my calculator. And then I'll say that about equals something rounded to 1 decimal place. All right, so fraction, and then I have even a fraction within that fraction. So 188 over 5, and then square, and then scroll down 1.8. And then press S to D to get this decimal. It's about 785.4 minutes. Okay, so that's number 7. On to number 8, the last one. Okay. So just to simplify these, so what I'm needing to do is I'm needing to distribute this negative. So negative 2i minus 1 minus 2i. Then negative 2i minus 2i is negative 4i minus 1. And it's typical, it's the problem, by the way, number 8 is asking us to leave everything. So the heading is basically simplify, and leave as a plus bi. So I'll just switch these around, in other words. So this is negative 1 minus 4i. We have a couple properties. The square root of negative 1 is I, and as a consequence, negative 1 is I squared. So I times